Hello again. Last time we talked about symmetries of a system. We're going to continue that discussion. This time, we're going to speak about something called a continuous symmetry. A continuous symmetry is a symmetry which, if the transformation is very little, it's still a symmetry of the system. For example, rotation of this circle. If you rotate it by an extremely small angle, it's still a symmetry of the system. The system remains as it is. If you rotate it with a very small angle again, the symmetry is still maintained. However, if you do the same thing to say a hexagon, okay, if this is your initial configuration with this apex up and you rotate it just a little bit, this is no longer a symmetry of the system. This is not a symmetry of the system. The system is no longer in the same configuration. So this is not a continuous symmetry. This is a discrete symmetry. This is what you call a discrete symmetry, and the discrete symmetry means that you can rotate it only by specific angles. The circle is special and you can rotate it by any angle. There are many systems in nature which, if you rotate or if you transform by very small amounts, if you transform in a certain special way, very small amounts, the system remains as it is. Okay, these systems enjoy something called a continuous symmetry. Now, continuous symmetries are extremely important. Continuous symmetries lead to something called conservation laws, and you have to take my word for this. Any system enjoying a continuous symmetry will have something called an associated conservation law. For example, if a system is invariant under rotation, okay, then the system will enjoy something called the conservation of angular momentum. Let's just look at it a little bit carefully. If you have a wheel of a bicycle, okay, and you rotate it just by a little bit, since it's a circle, it will keep its configuration. Okay. Also, since it's a circle and it keeps its configuration, that it enjoys a continuous symmetry, if you roll it along a surface, it will try to conserve something called angular momentum. In other words, it will keep on rolling as it is rolling. It will try to maintain the same speed of rolling. Okay, this will be explored in much more detail in the course, and this is just an introduction. So if you do not get this absolutely clearly right at the moment, do not worry. We are going to encounter this concept many times in the course, and I hope in a few lectures it will be extremely clear to you. Let me come to something which is very fundamental to quantum mechanics, and that is the identity of particles. Now, if I take a few balls from this ring that I have, okay, and these are, okay, okay, and these two rings might look absolutely identical to you, okay, but there might be a dent in one of them. Okay, I might write something on one of them and paint one ball with red paint or something like that, and I will be able to differentiate between the two. Okay, say I can see, you cannot see over there, but I can see a small dent in one of them. So this is different from this, and if you mix them up, I can still differentiate. Okay, this is, however, completely classical. That is, this is exactly how the macroscopic world works. In other words, if I give you two balls, you will be able to paint one ball red and another ball blue, and you will always be able to differentiate between them. Even though they are balls, okay, you will be able to differentiate between them. The same logic does not hold and is very importantly violated in quantum mechanics. Now, quantum mechanics, as you know, is a physics which is required to probe the ultra small. Quantum mechanics, it works through all scales, right, from small to the big. But when we get to the macroscopic scale, we no longer use quantum mechanics because it's difficult. But you cannot use any other physics for very small particles. So when we come to atoms, or electrons, we have no choice but to use quantum mechanics, because that is how nature works. So these two balls, okay, these two circles, if they were extremely small, if they were on the size of atoms, then these two, if these are the atoms, these two will not be distinguishable. You cannot paint one with the other. You cannot paint one with red and one with blue and differentiate between the two. Okay, if I mix them up, okay, I will not be able to tell which one is which. Just like this, and then I do something and you do not know which one was A and which one was B if I labeled them earlier. Okay, so the indistinguishability of a particle, or rather of particles, in quantum mechanics is extremely important. In other words, an electron is just an electron. You cannot have a blue electron or a red electron. An electron here is the same as an electron on the moon, and it's the same as the electron in Japan. Okay, that electron is the same electron in the morning and in the evening. There are no two electrons. The electron is just the same identical particles. Okay, it's the same electron, just multiple copies of it, and this is an extremely important concept to grasp. This leads to something called two types of statistics, or in other words, two types of ways to count them. For example, if I have to count these balls, I just count them off like 1, 2, 3, 4, 5, and so on. However, if I have a large number of these, huge number of these, okay, I will be spending a lot of time counting them, and that's not a good idea. So I will be defining something called density, and we will see how many balls you have per unit some volume, and you'll be multiplying that number with the total volume, and you'll get the number of balls, give and take a bit, right? They won't be exactly accurate because the density may not be uniform throughout, but give or take a few balls, that's going to be your figure as the number of balls, right? Now, the problem with quantum particles is that they behave funnily, okay, and there is this very important concept called spin, which we'll come to in later classes, but right now, just take it from me, there are particles, okay, which are so called spin half, and you'll get to know what this means in a class or two. There's something called spin half particles, and spin half particles are particles who are very non-cooperative. Electrons are spin half particles. So when we have something called energy levels, okay, places where these particles come and sit, you have one particle coming into one energy level, okay, and the second particle cannot come and sit on that same energy level. Okay, they are very uncooperative. This is a fundamental rule for electrons. Okay, this is in fact a fundamental rule for a class of particles. All spin half particles behave like this. In fact, it is intrinsically related to the fact that they are spin half particles. We will again come to know what spin half means in some time. Okay, they are called fermions. Okay, they are called fermions. Please refer to the lecture notes, and it's given in more detail there. They are called fermions, and they do not like to share their energy level with any other fermion. So fermions are by nature very uncooperative, which is fine. And then you have other particles who are pretty cooperative, and the cooperation means that several particles, the temperature is low enough, several particles can sit in one energy level. Okay, so if you have one particle, the second type of particle, if you have one of those particles in one energy level, and there's another particle which comes in, that second particle come in and sit on the same energy level. Okay, these particles are very cooperative. In fact, they are friendly to one another. Okay, and they are called bosons because they obey something called Bose-Einstein statistics. So these are the two types of particles you have in the universe. One, is a fermion, another is a boson. Fermions do not like to cooperate with one another. They have uh, they have a very uncooperative, selfish nature. The two fermions cannot be found on the same energy level, whereas two bosons can definitely be found on the same energy level. And the bosons are not spin half. The bosons are spin 0 or spin 1 or spin 2 particles. Okay, so integer spin particles, as in spin 0 or spin 1 or spin 2, these particles are called bosons. And spin half, or sometimes spin 3 halves, but we'll be dealing mostly with spin half particles are called fermions. Fermions do not like to share their energy level with any other fermion. Bosons like to share the energy level with other bosons. There is another very fundamental difference, and that is everything that you see around you. Okay, every part of your body, okay, this table, everything is made up of protons, neutrons, and electrons, right? They're made up of atoms, which are themselves made of protons, neutrons, and electrons. And each of the protons, neutrons, and electrons are fermions themselves. Okay, and it's very important for them to be fermions. Okay, it's the fact that they are fermions which make them so very rigid. Okay, rigidity cannot come from bosons. Rigidity can only come from fermions. It's also worthwhile to note that everything in the universe, every piece of matter in the universe, okay, right from stars to galaxies to everything that you see in the room to your own bodies, everything is made up of fermions, and just fermions. So fermions make up everything. Okay, they are the matter that you see. Okay, now what do the bosons do? You might think the bosons are completely useless, but you'd be completely incorrect. The bosons are the carriers of force. For example, the fact that you can see me is because there is light being radiated from the computer monitor, and it's going and hitting your eye, and that light is not carried by fermions, they are carried by bosons. These bosons are called photons, which are nothing but particles of light. And anything, for example, lightning, okay, the force that creates lightning, okay, it's carried by bosons. Okay, the magnetic force between a magnet and another magnet, whether it attracts or repels, they're carried by the exchange of bosons, in this case photons. Nuclear decay, and we'll come to this much more in the course, nuclear decay is because of something called of a class of bosons called the W and the Z bosons. Okay, and the most famous boson of recent times is of course the Higgs boson. The Higgs boson is not responsible for carrying any force, but it is responsible for giving mass to objects. Okay, so we've covered some very important things in this short video, and we earlier talked about symmetry. In this video I told you about what a continuous symmetry is and how symmetry brings in conservation laws, and we'll be exploring that much more in the course. We talked about indistinguishability of particles. In other words, particles are completely identical to one another, and we have two types of particles in the universe: fermions and bosons. Fermions are very uncooperative. They do not like to sit on top of each other, and they do not like to share the energy levels, and they are the ones which make up all the matter that you see around us. Electrons, neutrons, and protons are examples of them. There's another group of particles called the bosons, which are spin 0 or spin 1 or spin 2, and we'll be getting to know what these mean in some time. And they are force carriers. For example, the photon is a very good photon, or light particles. That's a very good example. You will encounter more bosons like the W and the Z boson, and of course you've heard of the Higgs boson. So that is more or less it. In the next video, we're going to talk a little bit about units that we use. Okay, and that is going to set us up for the future lectures. That should be a little bit of the groundwork that's needed for the current for the current topics. We're going to do a little more of quantum mechanics, but that will require you to concentrate on notes. And from the next video, we will be having those notes. So thank you and have a good day. See you in the next video.